Hello everyone. Today I'll be going over my project, making brain-to-text communication smarter with LLMs. This project is aimed at individuals who suffer from conditions such as ALS, paralysis, or other neurological or physiological conditions where their ability to verbally communicate is hindered. There are plenty of existing solutions such as the P300 speller board, eye tracking or gaze detection, and other custom software solutions. But they all typically suffer from the same drawback. They are slow and cumbersome. They have a low throughput of only 1 to 5 words per minute, and that doesn't allow the user to communicate in a real time conversation. Our solution is to harness the power of LLMs. Large language models have the ability to take a minimal user input of only keywords or even portions of words and generate highly expressive natural language suggestions. We also have the ability to enrich the LLM with context awareness. Um, the user may respond differently whether he's in a medical setting or a casual setting, and what the user wants to reply will heavily depend on what conversation he's a part of. So having a camera or a microphone gives the LLM additional context as to the situation the user is in, allows us to produce highly relevant outputs as compared to a typical autocomplete system. So this is an outline of our project. We have 4 main things that we need to figure out how to do. The first is reading an EEG signal. Then we want to convert the EEG control signal into some text input. That is what the user is actually trying to communicate. Then we want to capture the context surrounding the user, such as an audio or video feed. And lastly, we want to put everything together and generate suggestions based on that. Coming to the EEG headset part, I actually have an EEG device with me right now, and it's probably easier to put it on and show you what the readings look like. So what you see on the screen right now is the raw EEG values that are being outputted by the electrode that's placed on my forehead. You're going to see that every time I blink, there's going to be a spike in the readings. So let me go ahead and do it now. So usually those are unintended artifacts because what the EEG is really interested in measuring is your brainwave activities. But for our purposes, we'll be using the blink as our control signal. So I've implemented a very typical speller board here in Python. And when the character that I want is highlighted, I'll give my control signal, which in our case is a blink. So I want to say hi, I blink here, and then here. And now if I want to press enter, I wait till it goes to the last row, blink, wait till it reaches the last column, and blink. So this way we're able to turn our control signal into text. So now let's go back to our Kaggle notebook and continue from there. The first couple of cells are just environment setup. We are setting up our Google Gen AI client. And then we get to our context capture. Assume the user has a body-mounted camera and microphone. The camera will capture images at regular intervals and then feed that to the LLM. In our situation, we're just gonna feed in a local file and ask the LLM to turn that into a descriptive text. So that's essentially what this prompt is doing. I gave it an image of a physiotherapy rehab clinic, and you can see that the generated text is related to that. There's exercise equipment on the left, a treatment table, parallel bars in the center, a poster about physiotherapy, and as a whole, you can just see it describes the scene that it captures from the camera. So the system also captures audio context. So we feed in an MP3 file here, and then we ask it to generate a transcript. In this case, it is the physiotherapist asking, can you try to lift your leg? User input we capture from the speller board as we showed earlier. And in our case, the user's trying to say that his joints are feeling kind of stiff. He just simply inputs STIF from the speller board, and then we go ahead and start generating our suggestions off of that. So we feed in our user captured input, we feed in our context, which is converted into text, and then we have an LLM process all of that and generate relevant suggestions. So you can see that we have this giant prompt. All it does is it takes the image description, the audio transcription, and the user input and tries to generate 10 suggestions. We have them generated in a JSON, a strict JSON formatted output, so that we can do some additional filtering on top of these suggestions. So here you can see that it generated 10 suggestions in total. The first one is, I feel stiff today. It gives the reasoning for this suggestion, what line of reasoning that it followed. It gives a score for the contextual relevance and a score for the confidence. Confidence being how likely is it to represent what the user is trying to communicate. So once we have our 10 suggestions, we filter out the ones with the 3 highest confidence scores, and then the user picks between these 3. You can see with just a very simple 4-character input how you're able to get very relevant suggestions in natural language. So as a whole, it reduces the amount of mental exertion by the patient to generate natural language text, and the user is able to communicate more effectively with the system. So that concludes my project. Thank you all for listening.